Hi, Robbie.
Hi,
Hi. How are you? So
very
thank
good, very
you.
good.
Thank you. First, please accept my thanks, my gratitude for agreeing for today's webinar. And we are really excited to have you on board for this webinar. And we'll be starting in a couple of minutes. We are just waiting for a few more people, right? And by that time, we'll start by meanwhile we'll start. Preta, maybe we can start with the commercials. Uh,
Yes, sir.
huh.
Hi there. Hi, both of you.
Hi, Naval. Nice to see you
Hi.
again.
Same here. Nice to see you. Where I suppose it definitely would be an interesting session. It's something which embryologist waits for being a practical session. So,
Yeah, well, there's a considerable amount of content to cover, so it's a very wide topic.
right. I think definitely it would be worth your experience and developing it via also time lapse or so much of things you have in your, I think with you in your experience and all this, whatever you can cover, I think it would be of a great help for all the embryologists out over there. So definitely looking forward for the session.
Yeah, well, I think we've a very presentation covering how I would have managed troubleshooting in my own laboratory. And then I'm open to discuss any topic during the Q&A. So
True, true. That would be great. So as Ritesh sir mentioned, I think let's wait for just a few more minutes, and by that time, I think we have the introduction of IFA being going on, as it's from IFA. I think Sir Priyata is taking ahead with the commercials, right, sir?
Yeah.
yeah. And the sound quality is okay from your end, yes. Yeah, the sound quality on my presentation is coming through okay, yeah.
Yeah.
Yes, I
Okay.
Perfect.
The current scenario in ART training across the world is of observation only, which although gives you a fair idea of how the procedure is being done, but does not give you the confidence of performing it independently.
I just finished a visit to Indira IVF Group in Udaipur, India, and I'm totally impressed by several things. But one of the things that I'm most impressed of is the way they just prepare themselves for the future and how they're expanding. I'm here this afternoon visiting the Indira IVF Center in Udaipur. It has one of the most cutting-edge facilities that I have seen, including the perfect training for physicians and for embryologists. And I really think this is the future of how to train superb doctors and superb embryologists.
Embryology is confined not only to collection of gametes or making embryos, but it is about making euploid embryos to achieve a higher pregnancy rates. Embryology skills, lab culture conditions, gamete handling, and optimal environment are desired and necessary to achieve such results. The current scenario in ART training across the world is of observation only, which although gives you a fair idea of how the procedure is being done, but does not give you the confidence of performing it independently.
I just finished a visit to Indira IVF Group in Udaipur, India, And I'm totally impressed by several things, but one of the things that I'm most impressed of is the way they just prepare themselves for the future and how they're expanding. I'm here this afternoon visiting the Indira IVF Center in Udaipur. It has one of the most cutting-edge facilities that I have seen, including the perfect training for physicians and for embryologists. And I really think this is the future of how to train superb doctors and superb embryologists.
Embryology is confined not only to collection of gametes or making embryos, but it is about making euploid embryos to achieve a higher pregnancy rates. Embryology skills, lab culture conditions, gamete handling, and optimal environment are desired and necessary to achieve such results.
We can start with today's session. And so formally welcome everyone. Welcome to another session by IFA, another webinar, another Friday. We are together again. And I would request Naval to please introduce today's speaker and proceed with today's session.
Yes, Dr. Robbie, welcome very much. I think we in IFA are taking initiative where we are trying to train not only Indira embryologists, but to dissipate the academic sessions throughout the country, where the sessions are open for all the embryologists of the country. So with regards to the sessions which we generally have every Friday, we would be more than happy to welcome you today to our session, and really thanks and gratitude to you for accepting our invitation to share your knowledge to this group of embryologists in India. I would definitely like to mention that Dr. Robbie Kerr, who is basically PhD, and you would be amazed to understand that his PhD comes from developmental biology and embryology background. So that's something that, it's like right from the academic start, he has been into embryology, because even his post-graduation is basically from in assisted reproductive technology from University of Nottingham. So he has a vast experience, and the base of the starting itself is from hardcore embryology. He has over 20 years of experience in clinical embryology, and he has been one of the founding directors and the laboratory director at the Belfast Fertility, formerly known as GCRM Belfast, which is in Northern Ireland, which is the largest independent fertility clinic of Northern Ireland. As I mentioned, he has graduated from University of Nottingham, and his master's is itself in assisted reproductive technology. And he has also attained ACE certificate in clinical embryology, which is basically given by the UK Professional Training Scheme for Clinical Embryologists. And he did join the VitroLife group in 2022 as a clinical support manager for EMEIA to help establish VitroLife as a preferred partner for IVF clinic across the regions. He has been instrumental in a lot of decisions, and he has huge experience in the conventional culture systems, and at the same time also the time-lapse culture systems. So the topic which we basically have today, I suppose it would be a big plus to listen to his experience, and I hope this will definitely help all of us in our day-to-day routine embryology practice for the troubleshooting at the real ground root levels. So thank you, Dr. Robbie, to be here, and I would like to pass on the mic, the virtual mic, to you to further take it ahead from here.
Thank you very much for that very kind introduction. I will just load up the slides here, if you give me a second. So look, it's an absolute pleasure to be invited to speak to you all today about shall we say, a very broad subject matter, troubleshooting IVF culture media. and how to overcome poor embryo development. But before we start, I'll just declare, obviously, my conflicts of interest, as I think that's important. So obviously, I'm currently the Clinical Support Manager at Vitrolife Group for Europe, Middle East, India, and Africa. And I still am a shareholder of the TFP Belfast Fertility Clinic. And I'm also the Director of Advanced Embryology Solutions, who provide IVF laboratory consultancy services worldwide. And I'm one of the founding directors of Equigenesis Ireland, which is an equine embryo production facility based in the Republic of Ireland. So with that out of the way, we will start with a very short introduction. So I guess the key place to start is the functions of our culture media. Now, we can break this down into several areas. The most obvious is that culture media must fulfill the physiological requirements that we need in order to sustain the embryo during culture. And the media system, also together with the entire culture system, including our incubators and other equipment, must contribute to minimizing intracellular stress. Now, that stress can be metabolic, caused by incorrect pH, temperature, or osmolality. But of course, there are numerous other stress factors involved in the IVF process. We know that mammalian embryos can be cultured throughout the pre-implantation period in a number of different culture media and environments, but the resulting viability and the ability to implant and create a healthy live birth can be extremely different. Suboptimal culture conditions can cost the embryo with a significant reduction in viability. And the goal of developing any media system is that one enables the gametes in embryos to focus on the development and growth instead of fighting for survival. Okay, so with this in mind, something that is often asked is, aren't all culture media basically the same? Okay, and I would say yes, that, you know, to a degree, they have very similar components make up most commercial culture media, but they have different concentrations that have subtle differences in formulation. But actually, quite a controversial statement to start with is that I don't believe there is any such thing as poor culture media, okay? The only thing that we have is suboptimal use of that culture media within our laboratories. And this very interesting paper by Dean Morbeck actually analysed the composition of various single-step culture media from different commercial suppliers and showed that there were subtle differences in composition in terms of carbohydrates and amino acids. But interestingly, under the ideal conditions, they had very little effect on mouse embryo development. But when they started to culture the embryos in suboptimal conditions, particularly with respect of oxygen concentration, there were significant differences in the performance of the culture media. Which brings me nicely on to the chiral consensus. Now, the chiral consensus concluded that when we look at our culture system, there is only one thing that is truly important, and that is everything. And that brings me back to this idea that there is no such thing as poor culture media. There's only suboptimal use of the media within our laboratories. And I visit many clinics globally in my role at Vitrolife, and I see many different ways of working, and I see multiple clinics achieving significantly different results, but using the same products and very similar protocols, which leads us to look into the actual operations in the environment in which those labs are working. Now, we have to accept in IVF that things will go wrong, but it's how we respond to those things that dictate how we can improve our culture system and our embryo development. We have to identify the issue, investigate, find a solution, improve and monitor. And a fundamental component of doing that is what we know as the quality cycle. The quality cycle is a standard part of any quality management system. It forms a fundamental part of a laboratory achieving ISO accreditation. But this is where we recognize we have a problem in our laboratory or our system. We identify the cause and the solution to that problem. We implement that solution and we monitor the outcomes. Now, the only way we can monitor those outcomes is through having very robust KPIs in place. Now, key performance indicators, if we look at the official definition of those from Conatal in 2000, these are objective measures which are used in critical healthcare domains to monitor patient safety, effectiveness, equity, patient-centeredness, timeliness, and efficiency. They form a fundamental part of a quality management system and are important for the systematic monitoring of your laboratory performance in terms of both the procedures and the operating environment of the laboratory. And they evaluate your laboratory's contribution to patient care. So in effect, our KPIs are a way of checking how the procedure is performed and is that procedure delivering on the key set of objectives that we have defined. Now, we're very fortunate in IVF that actually we have an international consensus on performance indicators in ART laboratories, which was the Vienna Consensus report by the ESHRE Special Interest Group. And this actually set reference indicators related to the oocytes and proxy indicators of ovarian stimulation, and also performance indicators related to the fertilization and embryo culture phases. Now, they broke these down into both the competency level, which is the minimum level of performance that a lab should attain to reach, okay? And what they called the benchmark, okay, which was the aspirational goal, the gold standard in effect. Now, the gap in between these two values is what we would call the desirable range. So it doesn't matter if you don't reach the benchmark on every KPI, as long as you are in the desirable range in the middle and you haven't dropped below the competency level, okay? So obviously the KPIs, they set everything all the way through from numbers of eggs collected, ICSI damage rates, fertilization rates, cleavage rates, day 2, day 3, blastocyst development rates, biopsy rates, vitrification survival rates, KPIs for every part of the laboratory process. But the key thing when you think about your KPIs is if you are a clinic that treats a very unique patient population, maybe multiple failed cycles, lots of older patients, your KPIs will be very different from a clinic that maybe treats a lot of younger patients. And that's why it's really important when you analyze KPIs and identify problems with your culture media, you look at what we call the reference population, okay? So this would be female patients under the age of 40 years with their own fresh oocytes used, no donor gametes, using ejaculated spermatozoa only, so excluding any surgically retrieved sperm cases, no PGT cases, and looking at both conventional IVF and ICSI. These are your gold standard patients where you should be attaining the Vienna Consensus desirable range and all of these patients. If you don't, that is when you have a problem. Now, one of the things I often come across is maybe a clinic contacts me from somewhere in the world and says, oh, we have a problem in our system. And when we start to discuss with the clinic, they'll say, oh, we haven't had a pregnancy for the last 2 weeks. Now, I would argue that actually that is too small a time frame to identify if you have a genuine problem in your laboratory. Really, when you monitor your KPIs, you should be monitoring monthly and quarterly. And I'm going to show you an example on the next slide. So here we see an example as the title for the talk today was around poor embryo quality. So here we see a clinic performing over a 6-month period. So we see 4 months with a consistent blastulation rate, which is exceeding good quality blastocyst rate, exceeding the benchmark value or within the desirable range. However, in the month of March, we see a drop below the competency value, which is then followed by a drop in the preceding month. So that is basically what we call a double dip. And this is what would trigger an investigation in your quality management system. And this was the principle that I worked on in all of the laboratories I've managed throughout my career. Now, the first questions we must ask when we see this is, have there been any changes in both the lab and the clinical management of the patient? We are obviously in control of what we have done in our laboratories, but there are many other factors external to the laboratory which can have an impact on your KPIs. So it's important that you have a really close relationship with your clinicians from the outset so that you know if they have changed stimulation protocols. Do you have a cluster of poor prognosis patients coming through? It's important that you work as a team when these things happen to identify the potential sources. The next question you should be asking is, have there been any changes to the consumables, products, or batches being used in your laboratory of any product that has come into direct contact with gametes and embryos throughout the IVF process? As all of the equipment in the laboratory functioning normally, have you introduced either a new member of medical staff or a new member of laboratory staff, and there could be a training issue, or something which is often overlooked is significant environmental changes. Now, one of the clinics I managed previously was a very large public hospital in Scotland. We never changed a single product, same culture media, same labware, same equipment in the lab, same staff who had worked in the lab, and we saw an unexpected significant drop in our IVF fertilization rates. But we could identify no change within the clinic or the laboratory which could have contributed to this. As we were in a large public hospital, we then became aware that directly in the floor above us, there were some refurbishment works going on in another department. And actually what was causing the dip was VOCs coming from that refurbishment work down through the air system into the laboratory space. So it's really important that you think outside of your own laboratory. You know, we know that different times of the year we can have excessive temperatures, pollution indexes can be high, etc. So think about the variables outside of the laboratory. So after that short introduction, I think the first place you should always start before you reach out to your supplier and say, I think there's a problem with the culture media, the first place you need to start is the basics always. And that's what the middle section of the presentation today, we're going to focus a lot on these key variables: pH, CO2, temperature, and osmolality. Okay, now the control of these three parameters, pH, temperature, and osmolality, are crucially important for successful IVF. Not only is it important to be able to measure and control each one of these parameters individually, but we also need to understand that each of them will have an effect on the other. For instance, when preparing a dish with microdroplets, the osmolality in these droplets may be severely affected if this is done on a heated stage. Or pH measurements will be different if we measure them at room temperature compared to 37 degrees C. So it's really important that we understand these interactions. And furthermore, it's crucially important to remember that the sensitivity of embryos towards these three key parameters, pH, temperature, and osmolality, will change as development progresses. Now, this work from Whalen Gardner beautifully illustrates how the oocyte as a single cell is much more sensitive to stress factors compared to a well-developed blastocyst, due to the fact that it consists of a single cell versus a blastocyst which contains many cells. So many problems that actually occur in our lab, such as poor embryo development, we can actually trace back to day zero, where the effect has maybe been in a very early stage, which is causing the problem later on. Now, we know that in our lab environment, there are numerous sources of stress, and it's therefore critical that we understand how these sources can impact our embryo development and our clinical outcomes. The protein source we use, nutrient depletion in the media. Do you replenish the media, or are you just using a single step media all the way through to day 7? The types of amino acids that are used in our culture media. If we have too many amino acids, these can exert a negative effect. The oxygen tension is critical. It's widely accepted we should all be culturing at 20% or 5% oxygen rather than 20% to reduce oxidative stress. The timing of our embryo transfer, the over manipulation of gametes during the handling procedures, temperature, pH, single versus group embryo culture, the great debate which one is better. You know, we know from the mouse embryo system that mouse embryos do not like to be cultured in single embryo culture, whereas it's less clear with human embryos. And then one of the most important factors, which I will talk about in detail later, is actually that of the contact supplies we use, the culture dishes, the pipettes, etc. So all of these stress factors can have an impact on our embryo development. And moving on to a really important topic, let's discuss how multiple sources of stress can have a compounded effect. It's not typical that in any laboratory globally you have a stress-free environment for the embryos to develop. It just doesn't exist. So when we combine the effect of primary and secondary sources, we can appreciate that the combined, maybe amplified stress that occurs. So let's give you an example. So say ammonium accumulation in your culture media. That is our primary stress. It causes changes in gene expression, metabolism, decreased mitosis, and ultimately decreased viability following embryo transfer. Then we add in a secondary stress, i.e. culturing our embryos at 20% atmospheric oxygen, and we see similar alterations in the embryo's viability. Ammonium accumulation in the presence of high atmospheric oxygen, the two stress factors combine and are amplified, and we see the negative effects of disruption of glutamine and alanine pathways along with abnormal fetal development. And this illustrates how critical it is to optimize every single step of your culture system to prevent the combination of these stress responses. Because when we put the oocyte or the embryo into stress, it upregulates stress response genes. When it upregulates these stress response genes, it is switching away from what it should be doing, which is developing cell division. So it diverts its energies into defending against the stress rather than the normal cellular functions. And that's a very important concept. So we need to appreciate as embryologists that despite our best efforts, stress and its effects do have significance in our ART processes. And if we take into consideration these assumptions, we can now move on to the specific aspects of stress and how we can overcome them. So, focusing then on going back to basics, we'll start with pH and CO2. So, we know that pH is a measure of acidity or alkalinity expressed by the hydrogen ion concentration in a solution. And this is expressed in a logarithmic scale from 1 to 14. Acids are defined as substances that increase the hydrogen ion concentration, and alkali solutions are described as those that decrease that concentration. Okay, so the physiological pH range of most commercial culture media is probably somewhere between 7.2 to 7.4. Now, that actually may seem small, but if you actually do the maths within that range, a 0.2% difference actually means a 60% difference in the hydrogen ion concentration in that solution. So why is that important? So The intracellular pH, which is known as PHI, it plays essential roles in glycolysis and other metabolic functions, protein metabolism, cytoskeletal dynamics, cell transport, and epigenetic function. Okay, now embryos do possess mechanisms to regulate their internal pH, but this is an energy requiring process, and it has an impact on the cellular resources that are expended to do this. So pH and therefore hydrogen ions play very important roles in many metabolic and cellular functions, and it's critical that we maintain our pH in a very stable and narrow range. Now, interestingly, later stages of embryos actually regulate their internal pH more efficiently than cleavage stage embryos, which is probably due to the higher cell number and the tighter cell junctions. Okay, now critically though is the external pH, PHE, and this is derived from our culture media, and it is this PHE that we use to regulate the internal pH. Now, many people quite often talk to me about colour indicators in culture media. They prefer media brand A from media brand B because it is phenol red. But I think it's really critical just to highlight that we should never rely on these colour indicators in culture media. It may show you that visibly the pH is still within an acceptable range, but there could already have been a huge shift in hydrogen ion concentration before you will observe that colour change. So it's always a retrospective alert, okay? And it's also very subjective and open to errors in human interpretation. And also remember, when we're working outside of the incubator under atmospheric concentrations, we should always be using the correct pH buffer system, which is designed to maintain pH, seen as the atmospheric CO2 is only 0.02. Often I can visit labs where they say, oh, but we just use standard IVF bicarbonate media when we're doing ICSI because we're so fast at doing ICSI. But I mean, we have extensive testing data on this that shows even in 5 minutes outside of the incubator, you have a huge shift in pH if you are working in bicarbonate buffered media at atmospheric conditions. So really, we should always be using some forms of MOPS or HEPES buffered solution for our handling steps outside of the incubator. Now, why is the regulation of pH, why is it so important? As I mentioned previously, the later stage embryos regulate their PHI more efficiently than cleavage stage embryos, which is probably due to these tighter cell junctions. Now, interestingly, warmed vitrified embryos actually lack the ability to modulate their internal pH for several hours post-warming. And also denuded mature oocytes prior to ICSI also regulate their internal pH. So all of these stages are actually dependent on the culture media, the external pH, to control their internal pH. Okay, and that is fundamental because if we have an incorrect pH, we will see reduced cleavage rates, disturbances in cellular cytoscaling, alterations in cellular metabolism and energy production, all of which equal reduced viability. Okay, so the pH in the medium is critical for our mature oocytes, our embryonic blastomeres, and our embryos warmed post-vitrification. pH consistency in commercial culture media. Now, you would think that most commercial culture media will be provided with consistent pH batch to batch. But this really interesting study from Tara Homey et al. In 2018 showed that this is not really the case. Okay, so in this paper, they came to the conclusion that you should actually measure the pH of each new batch of media you get to make sure your CO2 level of the incubators are set correctly. But this would imply a lot of extra work and time. And we know that measuring pH is not easy and presents a lot of challenges. But you can see from the data from this study that between the different media, there were different levels of consistency, with some media ranging from a starting pH of around 7 to a max of 7.3, 7.2 to 7.4, whereas some suppliers actually were able to provide far greater consistency batch to batch. So be selective about your culture media. Test this if you can, look at it and check the variations that you find batch to batch in pH. So in our incubators, we know that the regulation of pH is controlled by a delicate balance between the ingredients of the culture media and the addition of CO2. Okay, and that the pH of the culture media is based on a physiological pH that creates an extracellular pH, PHE, of 7.2 to 7.4. And this is optimal for embryo function. Okay. And here we can see in this graph, actually, the different pH levels at different CO2 concentrations. So even if we stay within the physiological pH range, this can be over a wide range of CO2 levels, and there will still be a huge change in hydrogen ions. So each media lot is designed with an optimal pH according to the manufacturer, and you will find this on the certificate of analysis for your culture media. But you can see here that, if our gold standard is to be at a pH of 7.3, we're around about 6% on this graph. But when we remove our embryos from the incubator, so moving them to atmospheric CO2, you see that there is going to be a very rapid drop in pH as it starts to creep up towards the 20% CO2 mark. And vice versa, if we set our CO2 lower, we will increase that pH. And here, actually, one of the most common questions I'm asked is around how long should dishes be equilibrated for to reach the correct pH? And in the next two slides, we're going to look at CO2 first and then at oxygen. Now, to a large extent, this depends on the ratio and volume of media and oil. You can see two graphs here, each following the other. And the first line, we can see that we remove our media from 0. You see the time here along the bottom, and you see the pH. And as we place it from our freshly set up dish into the incubator, there's a very steep drop in CO2 pH initially. Then it really starts to slow down, and it's only really by 6 hours that we actually reach the middle of the optimal range of 7.2 to 7.4. So although you could argue you could use that dish after 4 hours, it won't really be at the optimal pH until 6 hours post-equilibration. Now, oxygen tension, on the other hand, moves in a much slower, diffuses at a much slower rate. So setting up a dish from cold media from the fridge, it actually takes 8 hours for that dish to reach 5% oxygen tension. So in my own laboratories, we never allowed a dish to be used before 8 hours of equilibration to ensure that the pH was correct due to the CO2, and that we had the correct oxygen tension in the culture media to minimize oxidative stress. But on the plus side, although your pH may move quickly when you remove a dish from an incubator, actually oxygen tension takes a lot longer to change. So if you remove a dish from the incubator at 5% oxygen, after, say, maybe 15 minutes, that dish will only reach a max oxygen tension of around 7%, which is still technically okay to work in. So, this is useful information to be aware in terms of planning how you handle your gametes and embryos on a daily basis. Now, we know that there are measuring pH is not easy in the lab. There are different ways we can do this, okay? We could do this direct. It's technically not as easy to perform and requires accurate equipment, i.e. a blood gas analyzer or a pH meter. If you're using a pH meter, you're going to need a calibrated electrode that works fresh calibration buffers. You have to have a protocol that allows you to measure at the correct temperature. And you also have to have consistent pre-incubation time and atmospheric conditions to produce reproducible measurements. The advantage of using something like the iStat, you can see pictured here from Abbott, which would be the pH meter, well, the blood gas analyzer I've used in my own laboratories. And the team here at Vitrolife, we use these routinely in the field for troubleshooting clinics, actually controls the temperature at which the readings are taking, which is very, very good. You know, gives a more reproducible measurement, it's easier to use, and it's consistent. Another point to remember is that if you're using a culture system where you add protein to your media, both the amount of protein you add and the type of protein you add will affect both the pH via the protein itself, but also via a dilution effect on the bicarbonate concentration in that culture media. So it's very important to think about that. Now, the other way of assuming you have the correct pH is through CO2 measurement. Now, this is easy to perform with a CO2 analyzer, but is an indirect measurement and makes the assumption that if you are at sea level, have 6% CO2, you should have the optimal pH. But you need, a lot of clinics we visit have these devices, but don't calibrate them regularly with certified calibration gas. If you use one of these devices in your lab, you should have certified calibration gases available that have a margin of error of 0.01%, okay, which allows you to check that the reader is reading accurately before you take a reading from your incubators. And once again, as with pH, it comes back to taking consistent, reproducible measurements. Now, very common is the use, as I said, the use of a CO2 meter in labs to get a reading of the gas inside the incubator, which then allows us to achieve the correct pH in media based on the manufacturer's recommendations. But as I'm sure you're aware, in India, you have vast geographies from flat plains to high mountains. So we need to be aware of the altitude of our clinic, and that will require an increase in the gas percentage. The partial pressure of gas changes with elevation, and that is why it needs to be increased. So when we move to increased altitudes, the total atmospheric pressure will decrease, and then the part of the atmosphere that consists of CO2 will decrease as well. A lower partial pressure of CO2 will result in less CO2 in the incubator, meaning that if I set the incubator in my clinic that is located 2,000 meters above sea level to 6%, in reality, I have less CO2 in that incubator than what I actually need to achieve the correct pH. Consequently, pH at such a setting will be too high and will not give good embryo development. However, the easy solution to this is that we increase the CO2 settings in order to achieve the correct pH in our culture media. So moving on to temperature. So based on biology, we perform all of our procedures at 37 degrees C, as this is seen as the physiological temperature, although there are some studies looking at culturing embryos at slightly lower temperatures of around 36.5. And my experience, and certainly in the published literature, 37 degrees C will optimize the metabolic processes and ensure that the embryo does not experience stress and doesn't have to compensate or adapt to its environment, okay? But we have lots of different equipment in our laboratory, which is temperature controlled. Heated stages, IVF chambers, incubators, heat blocks. And it's extremely important that we continuously validate the temperature of these surface areas and incubators to make sure that we are getting the optimal temperature in our culture media. And we should be using external validation probes to do this. Never rely on the display from a device itself. Now, We know that when the temperature surrounding our gametes and embryos change, it's going to cause disruption in the metabolic processes that could therefore influence their viability. Temperatures warmer than 37 degrees C actually appear to be much more damaging than lower temperatures, as the amount of damage caused due to a deviation temperature is dependent on the duration of exposure, as well as the temperature itself and the developmental stage of the gametes or embryos. As I said in the very early slides, oocytes, for instance, are much more susceptible to stress caused by temperature fluctuation than blastocysts. Okay. So in here, we can see in this study that we see 3 examples of oocytes that were maintained at 37 degrees C and subjected to 31.9 degrees C for 1.5 minutes or 21.7 degrees C for 5 minutes. And one can clearly see how the prolonged exposure to cooler temperatures can negatively affect development. And this study showed how important it is to have the best possible temperature control when we're handling our oocytes in day 0, as this is where we perform most of the manipulations. We have egg collection, denudation, ICSI. All of these temperature fluctuations, if our heated stages are not optimal, will have a negative impact on the meiotic spindle. And this was a nice study by a group in New Zealand, and they actually looked at temperature drops during the egg collection process on the clinical side. So they placed thermocouples at various places along the egg collection, from the tip of the needle, midway along the egg collection tubing, at the point where the oocyte drops from the tubing into the fluid, and then they measured in the base of the tube. And what was really interesting was that they found that the largest drop in temperature was at this point where the oocyte drops into the media in the tube. And this is the reason why we should have within our egg collection tubes a small amount of pre-warmed media, so that they're not just dropping straight into this tube that just contains heated air in a hot block. As you can see from the graph, that is where they observed the largest drop in temperature. So heated surfaces are one of the most challenging areas to temperature map in the laboratory. Now, we know that in our incubators, we have 360 degree heat. We usually have an external monitoring probe in there, which will be confirming we have the right temperature. But whenever we visit clinics globally for troubleshooting, because they have reported low fertilization rates or poor embryo development, the majority of times we identify one or more areas in the lab where the oocytes or embryos are being exposed to excessive temperatures. And this is one of the problems, because how we measure the temperature on our heated surfaces is where the great challenge comes from. So you can see the difference between measuring on a heated surface is that you have unidirectional heat coming from the bottom. The dish design varies from supplier to supplier. Some dishes have an air gap, other dishes are direct contact with the heated surface. So that surface ratio between the heated and non-heated surfaces in the dish, the actual dish setup, the volume of media, the level of oil, evaporation coming from the media, and heat radiation when you remove the lid to make an observation. So when we then place a probe into our culture drop, the problem is that the probe cools down due to thermal conductivity. The probe is not actually measuring exclusively at the tip, because the thermal conductivity interferes with measurement at the tip, which basically gives us a temperature gradient in that culture drop from the bottom to the surface. And that basically makes measuring your heated surfaces exceptionally challenging. So although we may think we have them set optimally, and I often visit labs with heated stages set at 38, 39 degrees C, And actually, where you're using direct contact dishes, you probably have 38, 39 inside that culture media if you measure the heated stage in the correct way. So it's important that we focus on the temperature in the media, not on the heated stage itself. Okay, different types of dishes will give different temperature profiles, which I'll come on to show you. And always measure the temperature with and without the lid, and also do some validations with and without oil, so you understand all of the extremes within your culture system. And it goes without saying, use an accurate, sensitive and fully calibrated thermometer. So we can see here actually just a comparison that was done at Vitrolife between different brands of culture manufacturers' dishes. And you can see here that actually different dishes have different temperature profiles when we just place them on a heated stage with a drop of media with no oil. And you can see that direct contact dishes give a better temperature profile. So if you actually look at this with a thermal imaging camera and compare these dishes, you can see that on this heated stage, which is set at 37, you can see that some dishes maintain a consistent thermodynamic profile compared to other dishes which have cold and hot spots. So when you think about the lab where you're going to use, make sure you try and use a single supplier with the same profile. So if you use direct contact dishes, try and use direct contact with the heated surface at all stages in the process. There are a few exceptions to that. Maybe when you're checking for follicular aspirates, you would maybe use a more routine standard IVF certified dish just because you use a large volume of them. But certainly post-egg collection, culture, denudation, ICSI, always work at direct contact and calibrate all of the stages for the direct contact dishes rather than the dish with the air gap. Remember, higher temperatures are more damaging than lower temperatures. The other problem we have is different types of devices that we use for temperature measurement. The most common one would be the T-type probe. This is the fine copper wire probe, which I'm sure many of you are familiar with. A K-type probe is a more robust type of probe for making an evaluation, but the gold standard would be a PT100, which is a platinum resistance electrode, which is integrated into the base of your labware that you use in your clinic to allow you to accurately measure the drop temperature in that culture drop. So if we do some comparisons between these probes, so this is an experiment that we conducted at Vitrolife, taking a thermocouple T-type, so the most common type I showed you here on the left in the last slide, and we actually inserted the probe into the culture media at different lengths, so 0.5 centimeters, 1 centimeter, and 2 centimeters. Now, depending on how much of the probe we inserted into the drop of media, we got completely different readings, which just shows you how inconsistent and prone to variation setting your heated surfaces is with this type of device. And taking this a degree further, we did triplet experiments against a platinum resistant electrode integrated into the base of a dish against a thermocouple T-type and a thermocouple K-type. And you can see that in triplet experiments, we found a variation ranging from 3.1 to 3.5 using the T-type probe, as the T-type probe exerts significant cooling effect on small volumes of media due to thermal conduction along the wire. So those probes are fantastic for measuring inside your incubator, 360-degree heat, but they are not designed to measure in a drop of culture media in a dish. The K-type probe is more robust, so if you have to use a fine wire type probe, I would recommend the K-type, as we could only measure a variation between 0.2 to 0.3 degrees C, but it is still a variation there. Whereas you can see using the PT100 probe, a platinum resistance electrode, you get far more reliable, reproducible measurements time after time. So one of the other issues that we can have in our culture systems is there are certain procedures that we carry out in our laboratories where we remove media from the fridge. We will maybe set up a dish and then we will leave that dish on a heated stage to actually warm up. Now, it's important that you as embryologists understand how long that process actually takes in your laboratory. And I've done a lot of work on this over the years, actually mapping and measuring, media from sort of the fridge, set up the dish, and then placing thermocouples into that dish and seeing how long that actually takes to reach the temperature that we require. So with a 5-well dish with a 0.5 mils of media or 1 ml of media, because the volume of media we use will affect the speed at which the dish reaches temperature, you can see here that it takes around 13 to 15 minutes from room temperature for that media to actually reach the correct temperature on your heated surface. So you should know this information for each of the heated stages in your laboratory. Vice versa, let's look at when we actually have an oil overlay over the top of that. So we can see here 0.5 mil of media with an oil overlay. It actually takes longer because the oil is slowing down that temperature loss, but we can see we're about 15 minutes to reach our optimal temperature when we place it on the heated stage. Then if you actually compare the difference between a direct contact dish, such as the 5-well dish from Vitrolife, and a standard NUNC 4-well, which has an air gap between the surface, heated stage set at 37 degrees C, you can see that we are reaching 36.3 degrees, but actually the temperature in the air gap dish is 2.3 degrees lower, and that it has a much longer equilibration time to reach the desired temperature in the dish. So the final one of our basic parameters is probably one of the most critical ones, and actually is another source of major problems in our embryo quality, and that is osmolality. Osmolality basically means a concentration of a solution in terms of osmoles per kilogram of solvent, in this case water. So here we see 2 droplets that have the same number of osmoles, but in a completely different weight of solvent. Okay. Now, this is important because all our culture media must provide tonicity, which allows the embryo to maintain cell size. Cells can maintain tonicity over a normal size over a range of osmolalities. Okay. Where we have a hypertonic solution, we have an influx of water and the cells are at risk of lysis. Where we have a hypertonic solution, we see an efflux of H2O from the cells, such as in vitrification or cryopreservation, and we see dehydration of the cells. But we really want to be working in this isotonic range where we have an equilibrium of movement of water in and out of the cells. So we know that all our culture media contains salts, amino acids, sugars, and other components that support embryo development. And in our cells, in a solution, we need to have the right balance of molecules, both internally and externally, to prevent this expansion and contraction. Now, from animal studies, it's believed that the optimal maximum osmolality to maintain human embryos is around 310 osmoles per kilogram of H2O. So we routinely culture our embryos in small droplets, and we know that evaporation of that media results in an increase in osmolality. We can reduce that evaporation through the use of an oil overlay, which is why we always work under oil. And I would, if you have any procedures being carried out outside of your laboratory, outside of your incubators, sorry, and you are finding that you're unhappy with your embryo development, make sure that all procedures are being carried out under oil, with the exception of searching through follicular aspirates and maybe some of the final stages in vitrification. Small droplets mean more care must be taken. Smaller droplets will evaporate quicker than larger droplets. So think about the volumes of culture media that you use in your setup. Think about the height of oil overlay over the meniscus of the drop. And all of these things are important. Humidified incubators can help further minimize evaporation, which actually leads me quite nicely on to the osmolality of culture media. So here we can see just from various companies' websites, you can see that all culture media have a range of osmolality. This isn't a problem. There's no problem at all. But what it means is you need to think about how you work in your laboratory and the type of equipment you have. For example, I used to use Sydney IVF media for many, many years in a previous clinic. But we would only ever have used that media in a humidified incubators because it has a very high starting osmolality. Whereas if you compare some of the other media here, they're all very similar, ranging 260 to 270 to 270 to 265 to 275. So you have a range of osmolalities, but understand what is the range in the culture media you use, and are you using the correct incubation culture system for that media system. Just another point on humidity. There's a lot of chat around how embryo development is better in a humidified incubator. Now, this is contentious, I think, because the studies that claim that sort of evidence have used culture media with a high starting osmolality. And actually, if you read the discussions in those papers, the authors themselves do point out that did they repeat the experiments using a media with a lower starting osmolality, they may not have seen the differences that they observed in those studies. So here you can see just a comparison with GTL media in a humid incubator and a non-humidified incubator. 180 microliter droplets. Starting osmolality in both media, both systems is 270 osmoles. By the end of day 6, in the humid incubator, you have a rise of 5 osmoles, and in the dry incubator, you have a rise of 10 osmoles to 286. Now, 286 is still way below 300, which is where osmolality starts to become a concern. But if your starting osmolality in your culture media is 290, you're going to be closer to 300 at the end of a 6-day culture in a dry incubator. So it's important you understand your media system. And just looking here, triplet experiments you can see here, that actually in a dry incubator, there is actually only a marginal 3.8% increase in osmolality over a 6-day culture. And then when we did mouse embryo cultures in the same culture media, we found that we had 40 out of 40 mouse embryos reaching the blastocyst stage in each slide, which is well above the cutoff limit of 80% in these experiments. So I mentioned that one of our main ways of controlling osmolality in our culture system is that we use oil overlays. And this is another area that I think clinics can focus on when they have problems in their system. You know, there are numerous reports in the literature of toxic oils being released to the market. Now, here we can see a video of a mouse embryo developing in one such batch of oil. And you can see it looks fantastic at this early stage, but look what starts to happen to the embryo post-compaction. So one of the things that you can look at when you start to see degeneration in your embryos or poor embryo quality in day 5 is have a look rather than the culture media at the oil that you're using, because we know that it's a significant source of toxicity in our culture systems. And this paper by Otsuki et al. From Fertility and Sterility in 2007 demonstrated this really well. So in the lab, they found a problem with embryo development and they wished to investigate the cause. And as part of their investigation, they sent the oil batches they were using off for hydrogen peroxide analysis. And the results showed an elevation of peroxide even in the unopened bottles and before the expiry date had passed. So they continued their investigation by studying the consequences of peroxide on fertilization and embryo development. And as you can see in the graph, with elevated levels of peroxide, we start to see significant effects on fertilization and embryo development, especially blastocyst development. Okay, so the authors summarized that the results strongly suggested that the toxic effects of the mineral oil they were using in their laboratory were due to peroxidation. And during this, they attributed potentially as being due to transport and or storage by the supplier and or distributor before the oil had actually arrived in the clinic. Importantly, significant peroxide elevation was detected in unopened bottles of mineral oil that had still not reached the expiry date. And the use of such oils in their system was associated with significant decreases in fertilization, cleavage and blastocyst development rates. So let's think about the type of oils that we use in IVF. The two most common types, mineral oil and paraffin oil, are both byproducts of petroleum distillation. Okay, the first one, mineral oil, is highly unsaturated fatty acid chains that contain many aromatic elements. Due to the fact that they have less saturation, they are more prone to photooxidation and generation of free radical species and equate to higher levels of oxidative stress potentially in the culture system. Paraffin oils, which are a better choice for IVF, are refined from further fractions of that distillation process and contain more saturated hydrocarbons. The more saturation you have in an oil, the less chemically reactive that oil will be, and you will have lower levels of oxidative stress. Then there is a third type of oil, synthetic paraffin oils. Now, these can actually be defined during production and can be engineered to have specific and desired properties for handling. They can be made non-toxic, have lower levels of VOCs, and can reduce lot-to-lot variation. So there's a really nice paper by the guys at Embryo Tools in Barcelona, where they compared 13 different oils from different manufacturers against a standard non-IVF heavy mineral oil from Sigma. Now, they found that there were significant differences in viscosity. So the most viscous oils, oil 2, 3, and 4, are full-on heavy oils, okay? These products are fantastic. I have used them myself through my career. They give you really good control of evaporation rates, osmolality, temperature, pH, but they are really not nice to handle. They're very, very thick. They're difficult to pipette, and a lot of embryologists don't like working with them. But there are other oils, as you can see here, oil 5 and oil 6 are what you would call medium viscosity oils, okay? Or sorry, oil 4 and oil 5 are medium viscosity oils, okay? And those give you some of the benefits of the more heavy oils, but have better handling properties for the embryologist. And the rest of the oils are conventional standard IVF certified culture oils. So in the experiment, they actually showed that the lowest change in osmolality, unsurprisingly, is with the more viscous oils, but the oil 4 and 5 still performed very well in these trials, but gave the embryologist the benefit of more usability, better handling properties. In terms of the daily evaporation rates, once again, these were the highest rates were observed in oils 2 and 3, the full heavy oils, But oil 4 and 5 were still performing better than many of the conventional oils. And in terms of embryo development, the heavier oils were performing well as well. So these types of oils, whichever one you use from whichever manufacturer, are a very good choice to help you control osmolality, but you just have to balance up how they work in your system. But certainly for the extended culture phase, which is where the largest degree of evaporation, change in osmolality will occur if you're working in a dry incubator, I would certainly use some form of heavy oil for your oil overlay at that stage. So thinking about dish preparation, and sufficient oil overlay is the most important factor. You must have enough oil in your dishes, okay? The size and surface area of the droplet has a huge impact on shifts in osmolality. Method of preparation of the micro droplets is important, as I'll come on to show you now. Work quickly and work one dish at a time. And you should consider the starting osmolality of the culture media you use. If you're working with a media with a higher osmolality, you need to be really, really tight on those setup procedures. So there's a really nice study by Jason Swain where they looked at the impact of different variables on dish preparation. Now, when I started as an embryologist, the very first job I was given was to set up all of the culture dishes in the lab. But this is actually the most important job and probably should be the last job we give to our trainees, because if it's done wrong, everything's wrong through the whole cycle. So the important factors that they considered in this study were drop size. So they looked at 10 microliters, 20 microliters or 40 microliters, setting up the dish with the airflow in the cabinet turned on or switched off, setting up on a heated stage or on a non-heated surface. And then they looked at what they called standardization. You place the drops down, you overlay with oil, or what they called the wash method. You lay the drops down, you put the oil on, remove the drop, and then replace the drop with fresh culture media so that you get no change in osmolality. And the data was really interesting from this study. So they showed that, unsurprisingly, setting up on a heated surface causes a significant increase in osmolality in the culture media. They didn't find a significant difference in airflow, but there was a trend that having no airflow resulted in a lower change in osmolality. The drop preparation method, the wash method, significantly outperformed the standard method, and actually using a small drop size of 10 microliters was significantly worse in terms of osmolality change than using a larger 40 microliter drop. So they then proposed what is the best and worst case scenario is what they can see. So your worst case scenario, your best control bottle you see here, and your best case scenario is a 40 microliter drop set up at ambient temperature with the flow hood switched off for airflow and using the wash preparation method, versus the worst method for dish prep: small media volumes, heated stage, airflow switched on, and standard drops down, oil overlay on the top. They then looked at the results in this experiment in terms of mouse embryo cultures at different osmolality levels. At 270 to 290 osmoles, embryo development is completely normal. But at the higher levels, there are very few blastocysts and hatching blastocysts. And when actually they increased the osmolality to 340, as shown in the previous slide, there were no blastocysts developed at all. So this is critical that we know that we have control on this osmolality. So if you are seeing poor embryo development in your culture system, this is one of the first places you should actually be looking, is at the setup procedures and the changes in osmolality in your culture media. So just a couple of concluding points on osmolality. Once the osmolality increases in culture media, you can never recover it, levels above 300 will have a negative impact on embryo development, so it's critical you stay below that level. Things that can also contribute to increases in osmolality is poor aliquoting of culture media into inappropriate containers. Here we can see, I see this quite regularly where people have taken an aliquot of say 1 ml of media to a 4 ml tube, placed it into a hot block to warm up, and then you see condensation up the surface of the tube. That's evaporation. That volume of media has evaporated, and you now have a completely different osmolality in that aliquot than you had. So if you do aliquot media, don't leave large air gaps. Use an appropriately sized vessel. We've talked about inadequate dish preparation, not enough oil, inappropriate handling of the media, i.e. a lot of things like if you're setting up dishes, don't remove all of the media from the fridge at once. Just take the bottle you need to set up your dishes that need IVF media, put it back to the fridge, get the next bottle. If you have a bottle of media in your fridge that has a very small volume in it, you've potentially got some evaporation will have happened there. Consider just opening up a fresh bottle of media rather than using that last 1 milliliter that's lying in the bottom of the media bottle. And also remember, as I said, if you're supplementing with protein, this can have an impact as well on your osmolality in your media. So oxidative stress is another thing we need to be aware of in our culture media, which can impact our embryo development. Oxidative stress is caused by reactive oxygen species, such as hydrogen peroxide, superoxide, and hydroxyl. As I showed you, peroxidation can occur in culture oil, which generates hydrogen peroxide, which is a free radical. These are highly unstable reactive electron scavengers, which cause damage to lipids, DNAs, and proteins by gathering up the free electrons that should be available to the cells themselves. In vivo, we have a natural protection against oxidative stress through our antioxidant complex, which works through deactivation, degradation, immobilization, and maintains everything in an equilibrium. But where we have a problem is when this equilibrium moves out of balance. So we have accumulation of stress factors, we have elevated oxidative stress, the antioxidants are depleted, and then we have excessive oxidative stress in our cells. This will result in increased embryo fragmentation, alterations to blastocyst gene expression, DNA damage, fluctuations in cellular metabolism, delayed cleavage rates, all of which are going to affect your clinical results. Now, we have multiple sources of reactive oxygen species in our laboratories. The oxygen tension itself is one of the biggest ones. So we should be working at 5% low oxygen whenever we can. Light exposure, even a short exposure to UV light, which is a component of visible light, is able to induce reactive oxygen species in your culture media and result in cellular damage, such as oxidation of bases and DNA strand breaks. An exposure of less than 5 minutes is sufficient to cause a major increase in hydrogen peroxide levels in mouse embryo cultures. The IVF media itself will contain many components that as the embryo metabolizes, things are consumed and byproducts are secreted into the media. These themselves will generate reactive oxygen species, and suboptimal plastics are an issue as well. So how do we avoid oxidative stress in our working practices? We should be always avoiding toxic and suboptimal culture materials. And I have a few slides on culture materials coming up. We should work fast and minimize time outside the incubator. If you're using time-lapse incubators, it's great because you reduce the number of interventions that you carry out outside the stable environment of the incubator. We should be working under low oxygen. We can use heavy oils to reduce shifts in osmolality. And then we should be storing and handling our media in the correct way. And then we can look at using antioxidants in our fertilization and culture media. Now, all commercial culture media contain antioxidants. So you can see here in this table a list of sodium pyruvate, sodium citrate, L-cysteine, L-arginine, taurine, EDTA, HSAA. These things all provide antioxidant properties in our culture media. But some culture media contain other additional antioxidants. So look at the composition of your culture media and see are the things you can do to reduce oxidative stress further in your culture system. So 3 antioxidants that are added to culture media are alpha-lipoic acid, which is being shown to significantly improve embryo development to the blastocyst stage and increase the cell number in those blastocysts. Acetyl L-carnitine, which improves oocyte chromosome structure, as well as blastocyst development and reduces apoptosis rates in the blastocysts. And then acetylcysteine, which is a precursor of glutathione synthesis and has been shown to improve cleavage and blastocyst formation rates. Now, what's critical here is that these 3 antioxidants actually upregulate GSH synthesis. Now, GSH is a fundamental component of our endogenous antioxidant complex, but it is low bioavailability. It is not soluble in aqueous solution, so it's a really poor candidate to add to culture media. But what we can add is the precursors that stimulate the production of GSH, and that's what these antioxidants do. So David Gardner's group did a multi-center randomized controlled trial on the addition of these 3 antioxidants to embryo culture media. Okay, and they evaluated 1,350 metaphase 2 oocytes in a sibling study allocating between media with the antioxidants and media without. And what they showed was that when you add the 3 antioxidants, there was a significant improvement in good quality day 3 embryos and a trend towards better blastocyst utilization rates. When they did a subgroup analysis on this data by patient age, they found that actually the clinical outcomes for patients cultured in the presence of the antioxidants was significantly improved in patients of advanced maternal age. And a more recent RCT looking at the same 3 antioxidants in culture media again has shown that when you add these 3 antioxidants to culture media during gamete collection, insemination and embryo culture, they didn't find a significant improvement in pregnancy rate from fresh blastocyst transfers in this study, but they did find that there was a significant improvement in fertilization rates and there was a significant improvement in blastocyst utilization rates. So from these data, it appears that the addition of the antioxidants is reducing oxidative stress in the culture system and actually helping embryo development. Now, depending on your own laboratory, you will see different variations here. If you maybe are working at 20% oxygen at some part in your process, having these antioxidants could be more beneficial in a lab that's maybe working in gold standard 5% oxygen with time lapse, you know, minimal interventions with the embryo. So think about how you work and could you gain a benefit from using these type of media in your laboratory? So just the sort of final few slides to wrap up the presentation here. So we're going to look now at contact supplies and quality control, which is another variable, which it's not always the culture media which is causing the problem when you see poor embryo development. You have to look at everything to answer this question. So in the IVF clinic, we have multiple components that come in contact with our gametes and embryos through the whole process. So aspiration needles, oils, micropipettes, labware, media, transfer catheters. And it's true to say that we are only as strong as the weakest link in that chain. And when we look then at this, so if we think we're using more than 15 items through a single IVF cycle, that is many variables that could be affecting our embryo quality. So we need to make sure as much as possible that we're not using toxic and suboptimal components during that process. And some really interesting point here is a thing called reprotoxicity, which was defined by David Gardner. And they defined this as the negative influence of the components on the physiology and viability of human gametes and embryos by resulting in reduced fertilization rates, impaired embryo development, reduced embryo implantation rates, and reduced ongoing pregnancy rates. And actually, in David's lab, when he was working in Colorado, they tested all contact supplies with an in-house mouse embryo assay before the products entered the IVF lab. And from these tests, they found that 1 in 4 batches of contact supplies were failing the mouse embryo assay. That's 25%. That's astonishingly high. And actually, Martin Nies then took this and did a further study which re-emphasised this point, although rather than using a mouse embryo assay, she used the human sperm survival assay. So she split the products into products used for patient procedures and products used for embryo gamete-related procedures. You can see 143 tests versus 207 tests, okay? And the results from this study showed that for patient-related procedures, 42% of the products that were being used were testing as toxic to sperm. So when you see a decline in embryo quality, it may not actually be something in the laboratory. It could be the gloves that are being used by the clinicians during the egg collection. It could be something in the oocyte collection needle, something in the tubing, the embryo transfer catheter. In terms of the products used for gamete and embryo-related procedures, they found that 10% of these were reprotoxic, the main culprits being the lid of the sperm containers, the culture dishes that were actually culturing the embryos in, and Pasteur pipettes that were being used for manipulation of culture media. So, if we think about this data, so if 25% of contact materials we use in our laboratories are potentially reprotoxic based on David's data, what are the chances of your system being unaffected by this? So if you have one suboptimal contact material, you have a 75% chance that your system will be unaffected. If this rises to 4 contact materials, that goes down to 32%. And when you get up to 10 or more suboptimal materials in your system, you actually only have a 6% chance that your system will remain unaffected by this. So it was concluded that almost a third of untested disposable plasticware in David's lab at this time in their QC program presented lots that were detrimental to mouse embryos, and 2 items that have failed that mouse embryo test would have directly entered the laboratory and come into direct contact with gametes or embryos. Now, fortunately, we've moved on a long way since those initial studies by David, and we now have products which are fully certified for IVF use. Okay, IVF, they are intended for IVF use and intended for the gametes cultured within them to be transferred back to the human body. Okay, but when I visit labs globally, I still find dishes in use in many clinics globally that are only marked as an in vitro diagnostic. An in vitro diagnostic device is not tested the same way as an IVF certified device is. So although you can culture gametes, etc. in it, anything that comes into contact with that IVD device is not intended for transfer back to the human body. So it's important you understand these fundamental differences between these classifications. Now, if we look at the actual quality control process through medical device production. Okay, now I base this on how this is done at Vitrolife, because obviously I work for Vitrolife, but we secure stable and reliable raw materials and deliveries by evaluating our suppliers several times a year. We also review criteria such as delivery precision, expertise level, and code of ethics. Secondly, we then selection of the best material. We do stringent testing on all of the raw materials to eliminate variation. So we always perform extensive mouse embryo assay in the raw material lots. So only material that passes that QC can be released to the manufacturer of the final product for the consumer. Third, the manufacturing environment itself meets the highest possible standards. The quality control system is in place. It's regularly audited by external authorities. And then we have extensive testing on the final product. Now, this is where the variation comes from supplier to supplier, because not everybody tests final product the same way, okay? Everybody does a mouse embryo assay, okay? That is the industry accepted standard, but there are many variables which can affect the outcome of a mouse embryo assay. The strain of mouse you use, 1 cell versus 2 cell, the type of media you use, the culture conditions. If you use a simple, really basic media, you will have a higher degree of sensitivity in that mouse embryo assay than using a conventional culture media with lots of things that will compensate for something that may be suboptimal in there. Then you need to have acceptance criteria. Are you only looking at blastocyst formation rate, or are you looking at morphokinetics and looking at final cell numbers? And then looking at the test method itself, okay? Are you using a culture system which puts the mouse embryos under stress, i.e. single culture and microdrops, then adding in, you know, your suboptimal component? Potentially they are highly susceptible to that variation. So if we look here in this slide, we can see that the regulatory requirements for any IVF product is that a mouse embryo assay is performed. And this is the FDA guideline, states that you should have greater than 80% expanded blastocyst. So the industry accepted standard, therefore, is 80% expanded blastocyst. The way we test in vitro life, we look for morphokinetics, so we look at compaction at 47 hours, we look at early blastulation rates and expanded blastulation rates at 96 hours, and we look at average total cell number compared to the control group. This gives you a much more sensitive assay that exceeds both the regulatory and industry standards. And if we look here, this is a really interesting analysis here. So we can see the coloured line you can see is the 80%, which is the only requirement from the FDA guideline that a product should meet before it's released to market. So in the first test, we were comparing a recalled batch of media from another supplier against our mouse embryo assay. So the first test you see is 3 20 microliter drops with 10 embryos in each, and that is the Vitrolife standard mouse embryo assay. And you can see that brand X, as you can see here, failed to meet the minimum FDA requirement of 80% blastocyst development at 96 hours in this assay, okay? The second test, individual culture, which you can see, is designed to be I'll just put the laser pointer on so you know where I'm looking. So this second set of graphs here relates to the individual culture, designed to be a really sensitive assay. So the embryos are cultured individually to closely mimic human lab conditions, and culturing mouse embryos removes the paracrine factors and recreates a very sensitive assay. And as you can see, the GXTL passes this assay, whereas the recalled lot fails that assay, okay? And then we look here in the final set of graphs at the FDA minimum guidance, okay? And here is where you see how that batch of media was released to the market, because it passes the 96 hours greater than 80% blastocyst formation rate. And this is critical that you understand that not all culture media are tested in the same way. So you as an embryologist should always be scrutinising how the products you use in your lab are tested to ensure that the quality of that product when it reaches you is critical. So just a final couple of points on storage and handling of culture media, because this is another variable that's often overlooked. So when media is delivered to you, you should be looking at the optimal transport of that media should be at 2 to 8 degrees C, okay? In my own laboratory, when a shipment of culture media arrived in the lab, before we opened the box, we would place a temperature probe. We had a long metal temperature probe. We put a small hole down through the polystyrene box, and we measured the temperature inside the box before we opened the media. If it was outside of range, it went back to the supplier and we asked them to ship us another shipment of media, okay? So you can have a short-term, there can be short-term spikes up to 20 degrees C in any media shipment, and that is acceptable. But you should have, your media supplier should be carrying out stability studies, which shows that with 13 degrees C, so if the temperature got as high as 13 degrees C in that media shipment for 7 days, then the normal storage and the normal storage for the shelf life of that product will still be okay to use, okay? You should have accepted transport conditions from your supplier. In our case, it's 7 days of transport from when it leaves the factory to getting to the distributor, but then you may have another 7 days sub-distribution in your case. Basically, we're looking for less than 12 degrees during that shipping, and you can have spike accursions, intermittent ones up to 20 degrees C, and you shouldn't see any problems with that culture media. It's where you see prolonged exposures to higher temperatures. If you have issues with temperature, then there will be further investigations by your supplier. But what you have control of is how you handle the media when it arrives with you in the clinic. So if your media comes in cardboard capsules and boxes, don't remove the media from those boxes. Those are there to protect the media from the light, because media is photosensitive. If you can switch the light off in your refrigerator, do it. Or even better, just use a refrigerator with a solid door rather than a glass door, so that the culture media is never exposed to UV light. Make sure you use a medical grade refrigerator. Domestic refrigerators do not control temperature the same way as a fan-assisted medical grade refrigerator will, because it will be an even temperature distribution throughout that refrigerator. Think about how many times the refrigerator in your lab is opened and closed each day. Can you design how you do your setup procedures to minimize those door openings the same way as you do with your incubators, and have temperature monitoring in place? Manual temperature monitoring of a fridge, putting a probe in it, is not acceptable. You should have 24/7 temperature mapping on your fridge happening at all times, so that you are aware of if there has been a temperature issue with the storage of that culture media. So the key thing is, once you've gone through all of these variables that we've talked about, and you are then happy that, nope, there is definitely, we've measured everything, we are compliant in our lab, this is the point when you reach out to your supplier, and we will then do an analysis at our end in terms of the batches of media have probably been shipped to multiple clinics globally, and that's where we can collect in the data of any reported incidents with the same batches of media, and we keep all this data on file. But if you haven't looked at all of the parameters that we've spoken about in this presentation, then that is what your supplier is going to ask you. Have you looked at this? Have you looked at that? To ascertain why you may have a problem with embryo development. But all suppliers will work with you to identify where those issues are. So never be afraid to reach out to your supplier if you think there's a problem. So with that, I'm going to conclude back where we started this presentation, okay? There is no bad culture media. There is only suboptimal use of that culture media. And the one truly important thing in your IVF laboratory is everything in terms of troubleshooting poor embryo development. And with that, that's the end of the presentation, and I'm happy to answer the numerous questions I've seen popping up in the chat as we've been speaking.
Thank you, Robbie, for such a wonderful and enlightening session. Indeed, the last line you said that there is no bad culture media. In fact, that is very true, and it is not the culture media which is bad. It could be the culture conditions that get bad.
Correct.
And,
Correct.
And you were very, I think you were very successful in explaining all the things, and especially pointing out the vital role of osmolality as well as pH in giving good embryo, rather good blastocyst percentage. And the most vital is optimal temperature, optimal CO2, and RH. That should be
Yes.
maintained. That is a must. Rather, so
Yeah. No, absolutely. I mean, every lab I visit globally to do troubleshooting, we spend a lot of time making sure that they have those basics correct. I mean, if I was to say probably one of the most important pieces of equipment that I think any IVF lab can purchase is not the shiny new best of the best incubator. It's actually a blood gas analyzer. It is the most powerful tool you can have in your laboratory. And if you can, having access to an osmometer is incredibly useful as well, because when you experience a problem, it allows you to actually get an osmolality measurement. Have actually you got a shift in osmolality over 300, and then you can go trace it back, really scrutinize your setup procedures. But actually many clinics are not in a position to invest in that sort of equipment, but we can go back to how we set up the dishes and go back to first principles. And I know from my own experience in one of my laboratories I managed through my career, I had a lot of staff coming from different clinics at different times. You know, we had a turnover of embryologists. And although we had very clearly defined setup procedures, we noticed there was a decline in our embryo development rates 1 quarter. And when we looked at it, we found that one of the new embryologists that came in, despite being trained on our setup procedures, had just gone back to how she used to set up in her old clinic. And that in any dishes, because there was no pattern to it. It was very inconsistent. It could be up, it could be down. And we identified that actually, and the way I was able to do it was by looking just at the weekends where the embryologists had worked, where there was only one embryologist working. So they had set up every single dish for the next day. And we could attribute the drops to the cases that were done following that weekend. We did a little bit of retraining, problem solved. So, you know, sometimes it's just looking at the basics is the way you need to go.
True. I think most of the time it's the basics which people fail or they forget, and then later on just they focus on the bigger techniques and they just leave the smaller techniques onto the junior embryologist, and that too without training them, just letting them know the SOPs, and that is where the problem starts because they just follow the SOPs without the scientific reasoning behind them, and then the lab culture conditions starts getting screwed up. So
Yes.
that's how generally it all goes. And I think on the same lines, we do have questions in the chat. You must be knowing, obviously, the questions started popping as and when you were already taking the session. So the first one is very small and simple. Why we make small droplets? I think most of the IVF centers do use small droplets for culture. And then We know that the larger droplets has a less change in osmolality and the smaller ones have the higher change, as you also showed in the presentation. So still, I think that's something which is convenient. What's your view at it? Why do we make small droplets?
Well, if you actually think about it, I would argue that every clinic in the world makes small droplets. What size of droplet do you use to do ICSI? Probably a 5 or 10 microliter droplet to carry out ICSI, embryo biopsy. That is a small droplet. And if you set that dish up in the wrong way, the osmolality will change in that media and you will put a stress on that oocyte at the most sensitive stage on day 0. So actually, we all use small droplets at some point in our IVF process. In terms of culture, I've worked with many different culture systems over the years. I was involved in a project many years ago with Henry Leese at the University of York, looking at amino acid turnover in spent culture media using HPLC chromatography. And in that study, we were using 5 microliter individual culture drops for the embryos. But the way we avoided the evaporation in that setup was by using a 4-tip multi-pipetter. So we laid down all 4 drops at once. We had a tube pre-aliquoted with 8 mils of oil. As soon as the drops went down, the 8 mils was poured directly on top of the dishes within a matter of seconds. But fortunately, we don't work. That was very specific to that project because they needed tiny volumes of media to detect the amino acid changes. I think generally it's accepted that people try to avoid small drops, even if they're working in individual culture. If you think about an embryoscope slide, that is 2 wells. Each well contains 180 microliters, okay? And then you have 8 embryos in each of those wells. So that's 20 microliters per embryo in effect. So the smallest drop size I've ever worked with is a 20 microliter drop.
Oh, great. So smallest is 20 microliter. Embryoscope obviously has those mechanisms to have a well kind of structure, or some you do have a group culture, but still it's an individual culture.
But still
and I think
individual, yes.
Yes. So that definitely helps, and that's something which are not possible. It's not possible in a routine culture dishes. I think majority of the people use 35 mm culture dish or 60 mm culture dish to prepare the culture droplets, or the 4-well dishes to have the culture droplets been made and culture the embryos in them. So I think in this particular situation, some go for single droplet culture or a group culture, and it depends upon what kind of culture systems they use and what SOPs they prepare, which is suiting to their incubator and their culture systems.
Yeah. No, absolutely. And look, there is no right and wrong way to set up a culture dish, as long as those basic 3 principles of pH, temperature, and osmolality are really strictly controlled. You know, if you're using a small drop size, you just need to set up really efficiently. One of the systems that I actually had in my last lab in Belfast was quite nice, where we had 2 people when we were setting up the dishes. So one embryologist did the drops, the second embryologist put the oil on. So the oil went on as quickly as possible, because I mentioned Jason Swain's paper there with the wash method of removing the media. That's a very labor-intensive way to set up, but you can actually achieve really good results by thinking about that. If you don't have the ability to have 2 embryologists, using your sort of 10 ml snap cap egg collection tubes before you've even started doing the media, if you know you're using a 60 millimeter dish, you're going to need an 8 milliliter oil overlay for that dish. So just have, if you've 10 of those to set up, have 10 tubes pre-aliquoted with 8 mils of oil, do the drops, then immediately pour the oil on, because there's a time lag between you then pipetting up the oil, adding that on to the dish, and that's where you see evaporation. And I say this all the time to every clinic, 1 dish at a time. Don't be tempted to do 3 or 4 dishes. You are not as quick as the evaporation rate on that culture media.
Right.
Because the
Yeah.
ambient air in the laboratory is in most laboratories, when you've maybe 5 or 6 embryologists busying around in there, all of the equipment, you're probably working in an ambient temperature around 23, 24 degrees, sometimes even warmer in labs. So the evaporation rate is affected by the environmental temperature in the laboratory as well.
Right, true. So the message is pretty clear to everyone. The embryologists, they do feel that they can be super quick, but it's not like that. If you're alone, put across the media drop and put across the oil immediately with pre-allocated tubes of whatever number of dishes you have. And if you have two to spare at you, then one can put one can prepare the dishes and second one put in the oil as early as possible so that the osmolality doesn't change or the evaporation is not affected.
Perfect.
Great.
And I think just one final point there is, as I showed in look at the culture media you use in your laboratory and understand the starting osmolality of that media. And that is also key. Right. If you have a high starting osmolality, use humidified incubation. If you have a standard 265 to 275 dry incubation, but you can get better results probably by using a heavier oil, which I guess leads us on to the next question nicely.
Right. True. So again, yeah, that's something which is a very important point you made. You choose the incubation and choose the media according to your incubator. It's a dry incubator, you can have a lesser osmolality, and that's something which these days embryologists are not looking at, that looking into the product details, the IFU, and look at that and accordingly decide what you have to do. So study the components or the products which you are using and accordingly prepare your SOPs or the incubation. And you have already mentioned with regards to oil also that yes, the heavy oils are the one which I think you would recommend, which is the next question which you have answered, right?
Yeah. So I mean, my experience was I used standard oils for a very, very long time, and we had really good results with standard oils. But every now and again, you got little fluctuations which could come into ambient temperature, changes in setup, subtle changes in osmolality. And we switched to using just a heavier oil for the extended culture phase. And we found that we got more consistency quarter by quarter in our KPIs. So certainly, and especially if you're using dry benchtop incubators without humidification, I would definitely consider using a heavy oil. Now, as I said during the presentation, there are many different heavy oils on the market and they all have different properties. Now, they are all really good products, but it's up to you to try them and find the one. I personally didn't like the really thick ones because they're very difficult to handle at setup. And we felt because it's quite time consuming, I was worried about evaporation on the oil because of the media, because of the time it took to set up. So I used a semi-viscous one, which was sort of sat in the middle. So I still got maybe not the benefits of the super, super high viscosity ones, but we still saw a tangible improvement in our culture conditions. And I think it's another important point, actually, and I don't want to diverge too much, but we operate these days that there is no ICSI coming for us anymore. This thing that's going to give us a 20% increase in success rates. We operate now in what I call the sphere of marginal gains. Can we gain 1% here, 2% by changing this? But if we combine all of these small changes together, can we uplift our success rates for our patients by maybe 6 or 7% by combining a lot of small changes together? And I think, if you change to heavy oil for culture, don't expect to see a dramatic change, but you may gain an additional blastocyst for each individual patient, then that is an additional chance at pregnancy for that patient. And therefore, it is worth doing when we look at things cumulatively.
Yeah, that's very important. Generally, people try to have the quicker ways of having success, and they fail to understand that with the small moves, like every drop fills up the ocean in a way. That is what you
Yep.
have to do when you want to have a larger success, because you can achieve a, a competency or a benchmark, but then if you have to move forward and ahead of that, all the small changes helps, where you have to do your pilots, you have to select your products, and
Yep.
even though the product is validated, still how it works in your system has to be understood by your own pilot, and then accordingly it has to be introduced, and that is when you can find the best potential of that particular product in your system.
Yep. Absolutely.
Right. Great. So with regards to that, I think there's one question which I feel is very much important. We are almost at the end of our timing hour, so we'll not go into every one of them. If you can quickly look at them and answer, but I would definitely ask one question, that is which Yukta has asked: how do you identify the issues? Like, is it in culture conditions or media or embryo? Because that's something you did everything right. Maybe you have done dishes at one by one, but still possibly there is a fragmentation on day three, or there might be some issues in the culture conditions. Now, where do you do the troubleshooting, and what do you look at it first to go get to know into the details of what can be the issue?
Yeah. So, I mean, look, I think if I was to follow this logically, so if I've seen an issue in my culture system, be that if it's fertilization rates, you're then going to be looking sperm related, you'll be looking at oocyte collection, something which people often overlook is, don't forget the denudation process, with fertilization rates at ICSI can be quite damaging. You need to have really, really tight temperature control of osmolality. So it's very difficult to pinpoint exactly where you would look, but I would start with, is all of the equipment that was used in that patient working properly? Test it, do your internal validations. Yes, the incubators were working. If other patients were cultured in the same incubator and had exceptional embryo quality, are you just looking at patient variation? So it's important, where you see a decline, extract the data, pull out the index patients first. And if the index cases, the good quality patients are doing well, have you just got a cluster? I've seen many times over the years where we've had just a cluster of poor prognosis patients all come through. And bizarrely, this always seems to happen. They do cluster together. So you maybe go, oh, we've had 2 weeks, and actually we've had poor embryo quality for 2 weeks. You check all of the equipment. You check if there's been batch changes in consumables. You check all your environmental variables, pH, temperature, CO2. Check all the heated surfaces. You check that there's been no changes on the clinical side. But when you actually extract out the patient population, you go, okay, so we've treated 30 patients in those 2 weeks. And actually 15 of those patients are on their 4th cycle without success now. So actually you have to always remember, get the data and the history from the patients first. And I think in a very early part of the presentation, I spoke about how it's critical that embryologists work hand in hand with their clinical colleagues to do these type of analysis. We should never work in silos. We should always be a team in our clinics. I know my learned medical colleagues will always say it's a lab problem, but
yes,
but a lot of times
that's global.
A lot of times over the years, we have identified issues when we've checked everything in the laboratory. We haven't been able to identify a cause, and then when we started to dig a little bit deeper, we found actually they changed a batch of gloves in the operating theatre, and that those were the cause of the problems that we were experiencing. So yeah, you have to be really, really tight. And actually, even not just with the clinical staff, I've always worked really tightly with my nursing teams as well, because ultimately they're the guys ordering the products that the doctors are using in the theatres. So they can be your early warning sign that something has changed.
Yes. I agree. We go 100% with you, because we also have had so many experiences being a global We have almost clinic in every part of India. And when it comes to troubleshooting, we look at it, and as you said, we go step by step, look at the culture conditions, look at the calibrations, then go back, look at the sperm and oocyte quality, go back, look at the other patients in the same incubators, and then you go back, maybe there are some patient conditions, and if not, then still at times we end up having being in a position where we're still unable to find what can be the exact parameter, and when we take it, or maybe it would be a patient parameter, and then we take it across. So there should be a flow chart, which basically a step down process where people should check in that, okay, if this is not an issue, then go to this, if not this, then go to that, then
Yeah.
not, then go. And if you have that in front of you, it helps you ease down your troubleshooting, and that is where at times you reach to the conclusions. Many a times you do reach to most of the times you reach to the conclusions. It's very minimalistic time that you don't reach to the conclusions, and then we are actually at hands of no one. It's just the counseling which might help the patients in that particular scenario,
Yeah.
and clinicians has to be best at it at that time then.
Yeah, I guess I always think when I answer these type of questions, the easiest thing is just to share a little bit of personal experience. And the most
Yeah.
recent problem I had was actually where we had seen an increase in damage rates with ICSI, and we were sort of looking at it. We started off, we checked the incubators, we checked the surface temperatures on the ICSI heated stages themselves. We couldn't find any issue at all there. But then what we did find was that there had been a change on the handling of the oocytes, something had
Yes.
crept into the protocol in the clinic around how the oocytes were being stripped at denudation. And we were able to make a
Yes.
tiny little change to our SOP just by adjusting the dilution on the high A's that we were using to make it less. I guess it comes down to an operator thing. Some embryologists were really quick and were able to expose the oocytes to a really short exposure to the high A's, and other embryologists were not so confident doing that. And our SOP maybe had far too many oocytes being denuded at one time. So we adjusted it, we tweaked the dilution of the high A's, and then we tweaked the number of oocytes that could be handled in a dish at any one time, and we solved the problem completely from that. So it's just following it stepwise. Check the equipment first, then check compliance with the SOP is critical, because if you have someone audit your embryologist regularly, I've done a lot of this over the years where you just sort of are in the lab in the background and you have a little checklist and you're just observing procedures and just making sure that there's full compliance with the SOPs. And on any given month, we would select a batch of 3 laboratory procedures at random, and then we would audit all of the embryologists on their compliance with the protocols. And it's a good thing to introduce as part of your quality management system is regular process audits, because you would be amazed the amount of deviations that are there. Now, I never do this as a sort of a criticism of my embryologist. Every day is a school day. It's all about learning and improving and what, I don't know an embryologist out there that doesn't want the best outcomes for their patients.
True. Definitely, definitely. Yes, we do agree, and yes, you should have backups of your medias also, your supplies also, and you should at times keep doing sibling studies to understand which is better, and you have to keep changing, as you also mentioned. At times, that is what helps us the most. Ritesh sir, I would like to uh, bring the mic to you. We are almost at the end of the clock cast, which was decided, and we still have a lot of questions and in the
But
chat
this
and
is,
questions. So
yeah, in fact, this topic is so interesting and it is so close to the for any embryologist's heart that anybody can just go on listening and listening, and especially when it comes from the Robbie, and everybody knows that he has mastered this thing, and you're the best person to answer these things. Robbie, just one question, last question from you. You mentioned that okay, if anybody is going to invest, the best investment is to go for gas cell, but blood gas
Blood gas
analyzer.
analyzer. Yeah.
So, Robbie, how practical is this for a small setup IVF centers? Do you really think that this is a must-have equipment in your lab? Because most of the companies and most of the senior embryologists, they have been saying that okay, if your CO2 levels are optimal, if your relative humidity is good, your temperature is good, you need not bother about the pH. Any comments?
Look, I can only share with you my experience. So I use the iStat blood gas analyzer in my own lab. Now, we had a combination of incubators that mixed their own gas running on pure CO2, pure nitrogen, and then we had some benchtop incubators running on pre-mixed gas. The variation between cylinder to cylinder was changing the pH in the culture media. If you're using commercially purchased pre-mixed gas cylinders, say 6% CO2, 5% oxygen, the margin of error on those cylinders sometimes can be as high as 0.4%. Now that is going to change the pH in your culture system, but you have no control over that because you're using a pre-mixed gas cylinder. So having a blood gas analyzer gives you the data to go back to the supplier and say, your specification on your gas needs to be better. So, I mean, when I was using pre-mixed gases, we always try to use the highest grade that we possibly could and had them certified to within 0.1%. It was basically, you know, our margin of error on them. But I have seen, I've visited labs where the calibrate, the certificate with the gas says plus or minus 0.4. And I'm like, well, if you plus 0.4, you've changed the pH in that from the optimal range. So yeah, I think a blood gas analyzer is critical. The other thing, we didn't use it for every new batch of every product, but when we changed our extended culture media, we always did a routine pH check on the extended culture incubator when we changed the batch of media. Okay, and just because, as I showed you in that study during the presentation, there are batch to batch variations. Different suppliers, those variations are small, but there are some suppliers out there where those variations are on a much broader range. So all of this was critical. And look, we can never trust, yeah, the CO2 6%, but CO2 sensors themselves move out of calibration. I know when my engineers would visit the clinic every year, they have to recalibrate the CO2 sensor in the incubator. So if it's moving out of calibration, your pH is gradually shifting as well. So it's a very useful tool to have. And another point is it's not just the lab that will use it. The clinicians in my clinic use the blood gas analyzer for doing pregnancy tests and all manner of, because you can test so many different things. You can even look at lactate concentration, glucose concentration in culture media. We had research projects running where we were using the blood gas analyzer to collect data. So, you know, and maybe, you know, in an organization such as Indira, you maybe don't need one in every clinic, but you could have them within the clusters that they are shared between clusters of clinics.
Right. That actually makes sense. And what about the small standalone centers? So would you still recommend them to have one?
I would. I mean, I think for any IVF clinic, you need to have the equipment at your disposal. You need an accurate calibrated temperature probe to measure your incubator and an accurate probe for measuring your heated surfaces. You need a blood gas analyzer and you need a CO2 analyzer, and that is the minimum amount of equipment, because when you have a problem, it is very difficult to troubleshoot without having that equipment available to you.
Right. That's a clear message, sir. So basically, we should have a CO2 analyzer, temperature meter, blood gas analyzer. At the time you were answering this question, there was a last question. I think one of the last questions also mentioned that, is there a difference when you shift a culture from dry gas to CO2 incubator after the XA is done. I think it answered indirectly when you said that different gas cylinders also have a different pH. So when you actually move from one culture condition to another culture conditions, there is a shift in pH and you never know how it gets affected. So it's better to keep them stable in a same culture conditions. Unless and until you need to do some troubleshooting, then only we can consider removing that.
I mean, I think it's routine. It's routine for clinics to move between incubators. I mean, it's very standard in many labs to do the egg collection in a box incubator because you need lots of dishes for the egg collection procedure. But then when you finish the egg collection procedure, you move to a bench top or a small where the embryos are in their own individual component. I sort of showed you and one the biggest issue is if you are using for egg collection a 20% oxygen incubator and then moving to a low oxygen incubator, you need to think about the equilibration time. So if the dishes were set up in the 20% oxygen incubator, they're going to take 8 hours to reach 5% oxygen when you move them to the low oxygen incubator, even though the temperature in CO2 is correct, but the oxygen tension, and that's a slow stress, and you now have gametes in that dish. So actually just have dishes set up in the low oxygen incubator, finish the egg collection and do a single move from 20% to 5% in one single step.
Right, so reduce it, minimize the movement, and do if you have to do it in a single step with the appropriate amount of equilibration for the medias.
That's great.
Perfect. Thank you so much.
What I would say is for the other questions there that I haven't answered, please send them through to me in an email, and I'm more than happy to answer them, send you them back just to share with the delegates as an email answer.
Sure. So if anybody has any further questions, you can just send us your questions, and we will email all the questions to Robbie to get them answered from him directly.
Right. Thank you so much. Thank you for being so generous. That's
No,
much appreciated.
My pleasure. It's I like to talk, as you probably detect.
Thank you, Robbie. Thank you very much.
That's fantastic. Thank you, guys. Have a lovely weekend, everyone. Thanks.
Thank you so much to you. Please do you also have a great weekend ahead, and hopefully let's work across if we have another question, because the discussions are always better and the discussions are more productive at times. So
I hope to be attending both the ACE Congress and the IFS later this year. So hopefully we'll see a few of you there. Okay.
Great. Sure. We'll be eagerly waiting to meet you. Thank you.
Thank you.